Hello, everybody. I've got what is that Bonnie Tyler song stuck in my head? Turn around every now and then I get a little bit something something. Turn around, bright eyes. Every now and then I fall apart. I want. I wonder if you can get a YouTube like what is that? Like the copyright takedown thing for poorly reproducing a song. Every now and then I fall apart, and I need you now tonight. I think my goal with this live stream is essentially to have something that I can look back on in 10 years and be incredibly embarrassed that I did that. So I hope you enjoyed my Friday karaoke. But anyway, happy Friday, everybody. Let's get started. I want to get started today, but first, I gotta set up my green screen first, so let's do that. I'm gonna set it up here. Thank you. Sorry. Okay. Keynote. Let's do keynote. Okay. So welcome everybody to my cool stuff live stream part 2, where we are cool stuff live stream where we're pairing with Aaron for an hour or so. Um, let's see, where is my keynote? Give me the keynote. Okay. So we're doing cool stuff live stream again today. Hi everybody. Happy Friday. It's Friday. I guess today is April Fool's Day, but I don't celebrate April Fool's Day because I'm a very gullible person and I thank you for laughing at my dumb jokes. Um I'm a very gullible person and I fall for everything, so I usually log off today, but I am not. I'm here doing some cool stuff live streaming. So happy Friday. Oh man, keep switching away from keynote. There we go. So last time we'll cover last time. We gotta do our Robert's rules of business here. We go through our old business and then we talk about our new business and then we have some motions, do different motions and stuff. Last time we had a special guest, and which was Evan Phoenix. Today we don't have a special guest. I think I have a slide covering that, and I actually really enjoyed having Evan on last time, and I want to have people on the stream in the future. But the setup that I had to do with him, like I really have to thank Evan because the setup was so complicated and I felt so bad putting him through all that. So I want to see if I can figure out an easier way to have guests on. We talked about tag pointers. I showed off this table, which was like the different like constants in the system, and we talked about how you could tell the difference between or how you could detect, given a pointer, can I detect whether or not this pointer is an object that I allocated out of Ruby's garbage collector, or is it something else? So we have to do a few different checks in order to do that. We also worked on an ARM64 assembler, and we're going to continue doing that. Like, I want to continue doing that today. I need to get the chat up here. Okay, good. Got the chat there. We're going to continue doing that today, and we looked at the ARM specification a little bit, and I'm just going to recap that here, because I mean, if we're going to hack on an ARM, keep hacking on ARM stuff, it's probably good if we recap how the spec works. So basically, like, if you look, ARM provides a PDF specification, but also an HTML specification, and so you can just view in your browser. But there's also an XML one, which we'll talk about in a little bit. So if you read the PDF one, you'll see this diagram, or the website too. You'll see this diagram, And the diagram, like every instruction in ARM64 is 32 bits wide, and every instruction in the PDF, it shows you what each of those 32 bits are supposed to be and what's encoded in them. In this case, this first bit indicates whether or not we're dealing with 32-bit or 64-bit registers. Here we can provide a shift. So this is a MOVZ, so it's like copy and immediate into a register. Right here we have a 16-bit immediate value, so that's the value that we're going to copy into the register. And then here's our 5-bit register value. So this is like we're going to copy 16 bits of data into, I don't know, X0 or whatever register we're going to copy into. So with 5 bits, that means we only have 32 registers, I think. 31. No, 32, because there's 0 there too. We started to implement some instructions. So this is the list that I had put up last time. Unfortunately, we didn't get to all of them, but we'll keep working on that this time. So this time, what we're going to do is, unfortunately, note, like I said before, we're not going to have a special guest this time, but I would like to have special guests in the future, and I need to figure out an easier way to have them on. We're going to look at an ARM64 assembler. Like I said, we're going to keep hacking on that. And I also want to show off, like, I'm going to show off some changes that I made to the repository since last time. And I'm just basically saying this so that I remember to show it to all of you. And then we're going to start, I think we're going to start with the MOVZ or MOVK. I can't remember. We're going to do one of these two, MOVZ or MOVK instruction. And then we're going to implement some more instructions. But what I'd really like to do is I'm going to do my best to take the last, like, maybe, I don't know, 15-20 minutes to I want to take this Ruby code, like this really simple method, and then see if we can translate this Ruby code or this simple method into machine code. But I want to put together like a kind of I don't know, framework so that we can do that in a more general case. So like, given a function, can I take this function and convert it into ARM64 machine code? Okay, so I guess let's get to hacking. Oh, Vinit, thank you. Was I always as funny? Absolutely not. You got to practice it, I think. Okay, where is OBS? OBS, there we go. What? Okay, and my display. Oh my goodness. Please pick the right display. Hold on a second. We got some like technical difficulties here. Let's do that. No. Why is my display capture not working? Okay. Let's just add a new one then. Display capture. Okay. And I want you to do this one. There we go. Okay, and for some reason it is too... Oh my god, I'm so embarrassed. I'm so sorry, everybody. Scale, fit to screen. Thank you. And then put me on the bottom. Sorry about that, everyone. I feel so unprepared. I'm like really caught off guard here. Okay. Yes, I love these headphones too. They're really good headphones. Okay. So let's do this. I want to show, so let's start off by looking at the changes I made to the repository since last time. If you want to hack on this, so if you want to hack on the ARM64 assembler, I have it up on my GitHub, and come here, I'm gonna bring one of these over here. No, don't switch. And no. Yes, that's nice. I have it up on my GitHub, and you can hack on it here. I made issues for every single instruction in ARM64. So if you want to try hacking on this and implement an instruction, like go ahead and grab an issue, and we're gonna do a few of them today, so you'll have like some examples about how to do it. And I just quit my thing. Oh my god. I'm sorry, everybody. My live stream today is like not the most professional. Let's go back over here. All right. Anyhow, let's get back in here and give me back the live stream. Oh my god. Okay. So I filed a bunch of issues for this, so we can take a look at the issues, and then if you wanna implement some instructions, please do it. So let's see. Changes I made. So I mentioned earlier that ARM provides an XML file for all of the instructions in ARM64. And what I was able to do is I made this. This is some really, really janky code, but I'm gonna show it off anyway because I mean I write janky code sometimes. But basically what it does is it goes through the XML file, so it like grabs a bunch of stuff out of the XML file and I had it generate all the instructions for ARM64. Now, unfortunately, it can't I'll just show you an example of one of them. So if you look in lib arch64 instructions, these are all the instructions, and let's just pick one of them. We'll look at add sub ext. This is what it looks like. And this stuff here, this def add, this is the stuff that I was able to generate via XML. So it's got all the things in it, like the binary template, and then it's got all the members of that binary template and shifted into the right position. But unfortunately, I haven't figured out a good way to generate the rest of this. So I had to hand code, this stuff here. Okay. So let's take a look at we'll look at lib arch64 instructions. Let's just pick probably some of the, I've been doing them in alphabetical order mostly, so some of these are probably not filled in. This is what it looks like. Normally it's just got this encode method, and then here's the instruction that's not you can see the template is written out here, but we haven't actually implemented it yet, so it doesn't do anything. Let's see. The other interesting thing. So I was also able to generate tests for it too. So if you want to hack on these instructions, most of the instruction is there for you already, and we have tests for them too. So if you look in the test folder, and this is please somebody help me with this. We need some better organization here. Basically, I put all tests for every instruction in the same file, which we probably don't want to do that, but I did. So if you go down, you can see a bunch of assertions. These are all ones that I implemented since last we chatted. But if you see these ones here, I got this skip where it says fix me, these ones need to be implemented. But I added the assembly pattern here. So this is the CMP instruction and the subs instruction. So this is what this particular test is for. Now, I found another way to be a little bit more efficient. If we look at so this is pretty fun. If we look at LLVM has tests for ARM64. And what's really cool is they have this if we look in here, there's a basic ls basic. What is it? Basic. Probably can't see this, so let's clear this. Basic-a64-instructions.s. So this file, if we do grep check in here, It's really interesting. Let's pipe that to less. Um, you can see like this is the instruction that they have. So this is the assembly, and then these are the bytes that you have to output. So with these, I've been able to generate some tests. So I can say like, for this given instruction, I need to ensure that I get these particular bytes back, which is nice. So I've been able to do like, if you see a bunch of these ones that are like assert bytes. Basically, I just took that test code from LLVM, ran it through a script. The script spit out these assertions. I pasted the assertions into the test file and then just went and did the implementation, which is like what we're gonna do. I think we're gonna do that today. I haven't the script that generates the test files. I haven't open sourced that yet. It's just local in my repository, but I'll try to figure out how to do that because I want to make this as easy as possible for people to contribute to. So like being able to generate all those test cases from LLVM would be really, like, I think really useful. The catch is though, like some of these test cases, so like, let's see, you can't just paste this in because this line here isn't valid Ruby code. Like this, like you could think of add as a method, x7, x11, all these seem like methods, right? You could make those method calls. But this one here, UTXH number 4, first off, that's going to be a comment, so we got to strip away that pound. And then the other issue is like we need to make sure, like precedence, right? We need to have parentheses either after the add or after the UXTH thing. So you got to do some munging on this data, which I'm going to figure out how to do that. I was able to generate some of that munging. I don't know, somewhere in here. But anyway, let's like write some instructions, I guess. So what do we have? We talked about mov-z and mov-k, but I think we only implemented one of them last time. And I was mentioning that like if you notice, each of the instructions is only 32 bits wide, but every register is 64 bits. So how do we get a 64-bit value into a register? And to do that, you have to use multiple mov instructions because we can only do 16 bits at a time. So essentially what you do is you say like, okay, I'm going to move this in mov-z. Z stands for 0. So it's like, we're going to copy the value into the register, but make sure that the register is zeroed out before you write into it. Then what else do we need to do? Mov-k is just like copy in there, but leave the bits alone. And we need to say, I got to shift you over by a certain amount. So you basically just like set the bottom 16, and then you have more instructions to set the top, the subsequent 16 bits. And of course, if you know that the top value, if you know that the top values are 0, you don't have to emit as many mov instructions. But anyway, let's see, which one of these did we implement? I don't remember. Oh my goodness, we implemented both of them. Did we though? Let's look at the tests. Test, basic test, mov-k. Like, okay, there's mov-k. How about mov-z? Mov-z. Interesting. So this is kind of interesting. Let's actually fill out this test case here. So it looks like we have probably mov-z and mov-k implemented, but there's this instruction here, this test mov-z. This says to me we have an alias going on. So I'm gonna pull up the mov instruction in here in the spec. Let's see. Some of these instructions make me laugh, like the names. There's one that's ROR, and it's like, that's how you know that Ruby works really well on ARM machines, because it has an ROR register, or an ROR instruction. This is gonna take forever. Oh, there's L. Okay. Everyone knows that we're doing this live, right? So, okay, there's Mauve. Where is Mauve? Like, okay. So, see, we have Mauve here. Mauve is an alias of Mauve Z. So, let's see. The encoding of this description matches that of Mauve Z. All right. So, the implementation for Mauve is the same as the implementation for Mauve Z. So, let's do like, let's see if we've got checks for Mauve in LLVM, because I just want to like generate these because I am lazy. Oh. Let's see. Yeah, there's some checks in here like these. So let's do that. Like I want Mauve, but I don't want all these other ones. And I'm not good at grep. So let's be like space Mauve. I'm sure there's like a good thing for word boundaries or something, but like I said, I'm not like super good at this. We want a space after Mauve because I only want these Mauve instructions. Mauve. Okay. Okay, that seems good. So let's do grep check, pipe, Ruby tilde, and this like I'm aware that I'm probably above this. You probably can't read this, but it's fine. You don't need to. It's fine. We're just generating these. Which one do I need? Not full tests. There we go. Okay, so that script converts all of these into assertions. So I'm just going to copy that. And then put it in here. So the script that I made that generates like yes, hi cat. I don't know if y'all can hear the cat snoring, but she finds this quite interesting. The script I made that generates all the instructions, it's not very smart. It just takes a look at the unique IDs for each instruction and just generates a class for that unique ID. And like clearly you see here, since Mauve is an alias of Mauve Z, we don't need two classes for that. But if we look, like I definitely have two. So like let's look Mauve Z. What's going on? Oh, it doesn't want to open it because I didn't write to the file. Okay, tag Mauve Z. So here, like this one's not implemented, right? Not implemented. But if we like, let's split screen and let's just do tag Mauve, or not Mauve, tag Mauve Z, tag Mauve Z. So here's Mauve Z. It is implemented. And if we look at this encoding right here, so if I take this, let's copy this line, Mauve Z, we'll copy it down here. Those two binary values are exactly the same. So these things are really the same, and it's just like I said, the script I used to generate all of these, it's not smart. Like it doesn't know about aliases, so it just blindly generated a copy here. So theoretically, I think what we can do is just like, if somebody calls Mauve, we'll just have it call Mauve Z. So let's do it. Let's do it. Let's just see if this works, and see if I got it right. Okay. What? Oh, come on. So there's Mauve Z. Let's just alias it and see if we're good. Alias Mauve Z. Let's see. Come back over here. What was our test name? It was Mauve Z. Oh boy, it didn't work. Why? Oh. What? That's not what I expected. I thought my build was green. Weird. All right. What is going on here? Mov-z, undefined method ampersand for registers here. Looks like we might not have implemented all of it. What line is this on? 2133? Okay. Yeah, one odd thing is like, I don't know how to get an ARC64 build on GitHub Actions. I think the default actions are all on x86. But yeah, I need to figure out how to get an ARM64 build. Okay. So we are failing on this very first line. That's like not encouraging. Okay, so it's mad because we didn't turn the register into an integer. Let's go look at that. Mov-z RB line 24. Okay. Oh, that's interesting. So this mov. Oh, I see what the problem is. So we have, in this case, we're doing a mov-z instruction between a register and an immediate, but this particular test case that we stole from LLVM, it's doing between two registers. So we got to implement that. That's just straight up not implemented. So let's do it. So we have I added these register classes. So you can see them defined here. Like here's register. And I added this predicate method integer to it, which I think is pretty funny. The reason I did that is because in IRB, you can do let's do on an integer, you could be 12.integer, right? And that totally responds to stuff. So with that method, we're able to tell it, we can tell the difference between somebody doing 30 versus somebody doing x30. So I can say, okay, well here, if the IMM is an integer, so if they pass an integer, then we need to do this integer one. Otherwise, we got to do something else, which is I have no idea what we need to do. I guess let's go take a look at the spec for mov-z. Mov-k, mov-z. So this is the spec between a register and an immediate, and that is not what we're implementing right now. We're doing between, oh, weird. Okay, well, I don't know what it's supposed to be. Mov-z, register, immediate. What are you supposed to do if it's not an immediate? I guess let's read. Oh, that's interesting. These two are SP registers, stack pointer registers. Okay, let's take a look. Let's see what the spec says. Okay. WD, is this allowed? Oh my goodness. It doesn't say SP is allowed. Usually if they allow SP, it'll say register or SP. Let's check up a little bit more. Mov N, these are all immediates. Is it supposed to be I don't know. It's so weird. Let's do this. Let's just see if we can make the test pass. Let's just call, if it's an immediate, if it's not an integer, let's try this. I don't know if this is legit though. Let's just call 2i on it. This can't be legit. Yeah, it's definitely not legit. Okay. What case is this supposed to be? Let's go look at the other mobs, I guess. Or, yeah. There's got to be a mov instruction that goes, here we go, mov to from SP. There we go. There we go. Move between register and stack pointer. Okay, this is the one we're looking for. So we have a form here, an encoding here for when we have a mov instruction and either side of it is SP versus like two SPs. Oh, interesting. Look at that. It's equivalent to an add instruction. Huh. Did not know that. So we should be able to say like, okay, well, let's do this. If either one of these is, so if, how do we say this? If one of these is SP, then we need to use the add instruction, right? Let's try it. Let's just try this. Okay, so if, how can I say this? Like, I feel totally on the spot here. If neither of them are integers. Okay, yeah, that's right. So if reg dot integer or imm dot integer, and I don't think that that's actually, that's not correct. Reg always has to be a register, so imm is sometimes an integer. Can't spell today. Okay. If it's not an integer, then it has to be SP, or one of these has to be an SP. And in that case, we're just gonna call add reg imm. Like, I think that'll work. Let's try it. Okay, what happened? It's mad because why? Add given to expected 3 on 2133. Okay, let's go look at that. 2133. Oh, come on. In add, oh, add wants 3. Of course it wants 3. Right, it wants destination, right, DNM, and ours is going to be 0, because that's what the spec said. The spec said that this is equivalent to 2 registers plus 0. Okay, let's do it. Oh, what line did we fail on here? 2145. Let's go check that. We made progress. So we're down here. We're adding, what is it? We're moving an immediate 98304 blah, 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 blah into the W3 register. So why is that breaking? Okay, let's see. So our expected binary is this top one, and our actual is the bottom one. It's interesting. So we have a wrong bit here, and we have 2 wrong bits here. Okay, but interestingly, this isn't dealing with the stack pointer at all. This isn't dealing with SP at all. This is just a straight up immediate going into an immediate that's going into the W3 register. Why is it wrong? Okay, I guess let's take a look. What does the spec say? Mov immediate wide. Moves a 16-bit immediate value to a register. We say SF, so in this case, W, since we were using 32-bit registers, this first bit's gonna be 0, so it's gonna be 0, 1, 0. Let's get the terminal and preview. Okay. So our expected is 2 zeros in a row. So this is actually the wrong instruction. Interesting. Why is that? Is there something about immediate that's like not good? OPC 1, so our expected is 0011, and we have we're clearly using this encoding when that's not right. What is the encoding it wants? 0, 0, no, not that one. 2 registers, really? But that's not, Inverted wide immediate, no. 0, 0, 1, 1. Oh, a bit mask immediate? How do we know that? I want to take a look at the test we got from LVM. So this is another like odd thing is I don't know if my script works that well. Let's take a look. Oh no, it's really, no, I don't want to run it through that. Pipe less. What is this? It's just some number, right? Mauve W3 983055. Let's see what the assembler says. So another trick I like to do is I've got just a sample assembly file here. So I just take these, put it in, and then see what does the assembler do. Let's do that. Obstump. No, not you. There we go. So we'll see what the assembler says. And yeah, it's like, okay, Mauve W3 983055. So it really like, so what I'm doing here is I'm assembling it and then using obstump to disassemble it. So the idea is like, if I'm not sure what the encoding of a particular instruction is or whether or not the encoding I'm writing is even valid, then I'll go check it. The annoying thing is though, it doesn't really tell me what form of encoding it's using, because clearly like when we look at this documentation, there's like multiple encodings for Mauve, right? So the kind of frustrating thing is I can't tell which encoding it's using. It's probably not that one. Not that one either. What did it say it wanted? It was like, we expected 0011 and our actual is 0100. So it's got to be a Mauve instruction that starts with those two. Can't be 00, can't be that one. Can't be that one. Mauve K? Nope. Because we got 3 ones in a row here. Mauve N? Nope. Mauve Z? No. Boy, I have no idea. Could be an alias for something. Let's skip it. I don't care. I don't care. I just don't care. Let's skip this one for now. Okay. Oh, I want to show off another thing I did since the last time. Okay. I'm getting too excited. Comment that out. So one thing I noticed is that I spend a lot of time doing def initialize like A, B, C, and then I have to do like, I'm one of the people that likes it like this, right? And then I know that there's some people that like doing A, B equals A, B, right? But I like it like this, and I notice I'm wasting a lot of time doing that. So I made my first like nice Vim script. If I do this, like, look at that. Oh, Alice and Bruno. Is it missing #0? I don't think so. Mauve Z is supposed to be like between a register and an immediate. And we have exactly that here. We have a register, W3 register, and then we have an immediate, which is just this number. So I'm not totally sure. Like, I will show you, let me show you something that John Hawthorne was very kind and helped me with the other day. Is I was looking at the CMN, I think it's CMN instructions. Let's look up there. Actually, we're coming up on the time. I want to start converting this stuff to machine code. We have enough instructions to do that. So we'll do some machine code, like Ruby to machine code instruction, or Ruby to machine code conversions. Where is it? No. What is feet mops? Why is preview not doing what I want? CILM register. So like this spec is somewhat terse. Well, I don't know if it's terse or very specific, but what's kind of sucky is you look at this and it's like, okay, you have this CMN instruction here and it does whatever, compare negative shifted register, whatever it does. We got these two, like it compares between two, or it works with two registers here, WN and WM. And if we look like, so, you know, technically the stack pointer and the 0 register, they're both registers. They're both really registers. But what I failed to notice is like when it says WN or WM, that's any register except the stack pointer or 0 register. So if somebody says CMN plus with the stack pointer, then it's a different encoding, and that's actually this, like one of these encodings. You'll see here, this is WN, WSP, so this is like you can use a register or the stack pointer, but with this one, it's like no stack pointer. You can't use it here. It's got to be a different encoding. So that's like a really, I don't know, for me that was like a gotcha. I was like really banging my head against this. I couldn't figure it out. Like this is actually the encoding we wanted to use. But John was kind enough to help me with that. Okay, let's comment this out. Okay, 24 up, D5J, get rid of that. We're gonna comment this guy out. Actually, maybe the rest of these will work, please. No, oh my God. 2151. That doesn't work? You're kidding. You're kidding. I'm gonna have to look at this later. I don't know what the deal is. Let's do some Ruby to assembly conversion. And now all of you on the live stream see why I need help with this. So please help me figure out what in the F is wrong with these instructions. I have to admit, like, I was able to generate nearly completely generate an x86 assembler, and it seems like way more of a manual process with these, ARM instructions. Like the spec seems a lot easier to read, but on the other hand, like figuring out which encoding you need to do, boy, I don't like. It's pretty hard. I'm somewhat struggling. All right, so I wanted to do like what I'd really like to do is I want to have a program that for a Ruby method will generate machine code for it. So let's say we have this method here, like method add stuff, A, B, and it just does A plus B. So what I want to do is I want to have a function that can convert this thing into machine code. So let's do that. Let's do it in a different file though. I will call the new file test2.rb. Def, okay, add things A, B, and A plus B. So we need to convert this. We want to convert this to machine code. And we can do this. We can do this, and we'll do it by disassembling this method. So let's do Ruby VM instruction sequence .of method add thing. So here we have the instructions for it. So we can look at this. Like let's look at the instructions. We can do puts iseq.disasm. Let's do that. All right, Ruby test2.rb. And I need to spell it correctly. Ruby VM. How did I misspell it? Oh, we're missing an N. There we go. Sequence. Instruction sequence. Thank you. Yes, thank you. I was missing the M or the N. All right, if we run this, we can see, we've got instructions here. So we've got instructions. We can access these. So we can say like, all we have to do is we take these and we can convert these into machine code. So let's do that. We can actually access, like if we do 2A on this thing, we can access all these in Ruby. So I'll do 2A. Actually, let's do a P because that's better than a puts. P. Let's do it again. P, Ruby 2A. And you can see here we've got all these instructions as Ruby objects. So we can do processing on them and we can go over each one of them and then we can convert them into actual machine code. So let's try, let's get a start on that. And what I really want to do is we're going to start on it this time. And I'd like to do, in 2 weeks, what I'd like to do is, I mean, depending on how far I get with this, now we'll do it. What I'd like to do next time is kind of more formalize how we do it, or how we do this conversion from Ruby's instruction sequences into machine code. And the reason I'd like to do that is I want to see if we can get at least a prototype JIT compiler working with ARM64. So see if we can at least get like a prototype working. Okay, so we've got our instructions here and as an array, but it's like an array of junk. And what is this array? Like, it has different information, but the main thing that we want is this, I think. What array is it? I don't know what index it is. Let's just try printing them out. Let's do p list. I don't know, 1. Oh. Or maybe, no. You know, we'll do require pp. Let's print it out like that. Okay. So we don't care about 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12. So we want the 13th one. This has our instructions in it. Is that right? That's like a lot. Okay, that's the right one. That's what we want. And I don't know what these two things are for. Well, I do know what these two things are for. These are trace point events. So, you know, if you use trace point, oh, come on, no. If you do like tracepoint.new : line, whatever, that will be fired here on this line. So that's what those are for, but I don't care about that. We're not going to do trace points. All we want to do is we just want to convert these things into, what do you call it? Machine code. So we're going to do a thing here. We're going to cheat a little bit, kind of, in that I want to generate a C function. So this is somewhat different than if we were really doing a JIT, because the C function is going to take parameters in a certain way. Like we talked about, I think last time we talked about the calling convention in ARM. So we have to be able to accept parameters via ARM's calling convention. So we're going to generate machine code that is a C function, and we're going to do stuff with it. So let's see. We're going to iterate over these. .each do instruction, and I want to do I'm going to do pattern matching on this instruction. Let's say it's actually, I'm going to shorten this up. INSN. What do we want here? So we care about arrays, and we care about arrays We don't care about these things. So we want to get arrays and the instruction out here. Okay, so let's try that. I have to say, like, I actually really like the this pattern matching stuff. So we want an array, and we don't care. It's gonna have 2 elements in it. So this is our like 2 element thingy. And then did we have a 3 element one? No, it looks like op plus is also 2 elements, isn't it? Okay. Oh, but leave. Look at that. Leave is like 1 element. Okay. So we'll do leave as 1. So we'll do this 1. So if we print out, oh, we don't want underscores because we don't want to ignore these. This is going to be the byte code, and this is going to be the operand, and then byte code. So let's do p byte code. We'll run that. Oh, no matching pattern. What did I do wrong? Hi, Hugo. Hi, chat. Why did I do this wrong? How did I do this wrong? Help me out here. Case INSN. No matching pattern. Oh, we need an else block. Right. Else. Don't care. Thank you, Tom. There we go. That worked. Okay. Let's see. So we got get locals, we got op plus, and we could look at the operands too, but here let's see, we got our leave. Let's run this. Run. Yay, leave. Okay. So for the get locals, like actually let's just match on get local. Man, I really do like this pattern matching stuff. It's quite nice. Oh, Allison says the docs say all these mobs are an alias to mov, but the shift will depend on the instruction variant. Could that be the problem? The shift is always being LSL16. Ah, yes. Yes. Allison, I think you are onto something. That sounds quite accurate. It could definitely be the shift. Yeah, okay. So thank you. Okay. So we're gonna do, dang, now I'm so excited about that. Thank you. So we're gonna do get locals. We care about get local, and we want to know the index of the get local. Man, I'm running out of time here. P index. Oh my gosh. I think I might have been like too optimistic on the whole get this done in 20 minutes. Okay. So the index, like you'll notice here we have an index of 4 and 3, and that's because I explained in previous live streams that these locals are actually negative indexes from the EP. So normally we have to index into the stack in order to get that local, and we have here 4 and 3. So those are like the first get local is at -4 and the second get local is at -3. So we need to like adjust these, and I'm just going to straight up hard code this in here. We know that the local table size is 4, so I'm just going to say p index. I'm going to say p4 minus index, and that'll give us our actual offset. So we'll have 0 and 1, and then we can say like, okay, well, we're going to get the first two, all of our parameters are going to come in via x0 through x. I forgot exactly how many registers are allowed in the ARM calling convention, but we know it's going to be like at least 0 and 1 are going to be our first two parameters. So we could say like, let's get our ARM64 thing going here. Yeah, we're going to include some registers. And then we can say like we want, I don't know, if we get these, like I guess we're gonna have to treat these as a stack. So we'll put them, what are we gonna do? we have to move these somewhere. We need to move them into a known location so that the add instruction knows where to find them. So like I've said in previous streams, like Ruby's virtual machine is a stack-based virtual machine. So when it's doing a get local, it's like getting that value, and then it's pushing it onto the stack. So it read it from a negative index and then it pushed it into another location. You know what we're gonna do? We're gonna treat our stack as x0 and x1. So we'll pretend that the top of the stack is also where our parameters come in, which means that we don't actually need to do anything. We don't need to do anything in here. Oh my goodness. This is a huge hack. And I am quite pleased. With it. Okay, so we'll do this. We're gonna pretend that x0 and x1 are the top two, values of the stacks, or the bottom two values. So if you imagine it x0 and then x1, x2, x3, x4, right? But those also happen to be the parameters that came in from the ARM, like the ARM calling convention parameters, which means that really all we need to do is we'd say like, okay, I'm going to take add. The add instruction is just going to take those two top instructions, add them together, and then push them back onto the stack, which should be x0. So this is awful. Let's look at our instruction for add again. Let's do p bytecode. I think it's going to be opt plus. Oh, come on. Ruby. Okay, opt plus. Yeah. So we have opt plus here. Oops. :opt plus. So our assembler, let's get a new assembler. We'll have an assembler here. And essentially, like, I'm totally cheating by doing this, but we can say like, all right, asm add the two topmost values, which we know those two topmost values are going to be x0 and x1. They have to be, because that's how our stack is set up. We'll say add. Actually, I don't actually know how the add instruction works. Let's go read that. As I have said on my Twitter, I did not prepare enough for this week, but isn't that the point of a live stream, I think? We're doing it live. ADC, no, I want add. Add extended register, so it's destination is the first one, and then the subsequent two are the registers that we're going to add together. So we're going to do something really odd here. We're going to do x0. So we're going to add into x0 the values of x0 and x1. And the reason I want to do this is because of ARM's calling convention. So ARM's calling convention states that x0 is going to contain the return value. So if we convert opt plus to do this, we know that whatever is at the top of the stack at that moment is going to be our return value. So we can actually just, in the case of our leave instruction, we just don't do anything because we know that that topmost value is the actual return value. I feel very like cheating. We can just do a ret instruction here. We can just return. I feel very cheating. This is not like, I shouldn't have, yeah. All right, so let's, now that we have that, let's write our assembly to a buffer. We need a JIT buffer, and then, boy, I'm totally cheating. So we'll write it to our buffer, and then we're gonna execute, we'll make the buffer executable. Right, I gotta do these two things because of security. Just gonna copy it from here. Write it to a buffer and then execute it. But in this case, our function is going to take two ints because we're adding ints together. And then it's going to return an int. I don't know why I had that there before. But anyway, we'll call it, and we're going to call it with, like, let's say, I don't know, Actually, let's break this out into a function. Adder equals this. Adder.call, and we'll just add two numbers. I don't know, like 5, 3, 6. Sure, let's try that. I don't know. Oh, I need JIT buffer. Let's see if this works. Let's quickly install this. Oh, oops. Thank you. Thank you. Yes, I'm missing an E. Told you I'm doing this live. There we go. We got our 11 back. So yes, I totally cheated. Like, let's look at that again. Let's do a quick little recap here and then call it a day and hopefully formalize this next week or in a couple weeks. We're pretending that all of our locals arrive in the ARM calling convention. So X0 registers through 1, 2, 3 or whatever, like whatever number of registers are allowed. We're also pretending that those registers are essentially the stack as well. So we're doing a translation between Ruby's stack-based virtual machine and the ARM like register machine. And we're cheating by saying that, oh, those registers, like the stack registers, happen to be the same registers as the ones that got passed in via the C calling convention. So what I want to do is, like, in a couple weeks, actually, let's go back to the keynote here. Keynote. And so what I want to do next time is, I'd really like to have a guest next time. So I'm going to figure that out. I think I don't know. I have a lot more fun when I can like talk to folks while I'm programming. I just think I don't know, I have a better time doing that. So I want to do that. And then I want to do more like Ruby to machine code translation, but I want to be more rigorous than this hacky stuff that we're doing right here. And the reason I'd like to do that is because I want to see if we can put together like at least a basic prototype of a pure Ruby JIT. I know we've already done a pure Ruby JIT with TenderJIT, but it targeted x86. I'd like to do it again with ARM, but I'd also like to try to come up with maybe a more creative way for us to inject the JIT into the Ruby system itself. Like, I have some ideas for hacks, and I want to show off those ideas and see what people think about the hacks. But thank you, everybody. I really appreciate it. Everyone, please have a good weekend. All right. Oh, yes. Yes, thank you, John. Add is commutative. All right. Bye, everybody.